Gotcha. All right. So guys, here we go. Today what we're going to do, and you guys are good? You got all the copies? Okay. So guys, let me set the stage for you for what we're doing today. And guys, this analogy that we've been working with, this idea of chemical reactions being like stories, I totally made this up on the fly on Wednesday when I was teaching this. And Miss Call and I have been sort of stewing on this idea over the last couple days. And guys, it's about to get even better. So join me. You don't have this slide and it doesn't matter. But guys, join me and let's talk. Here's where we are right now. We are talking about the idea that in the same way that a story introduces us to characters whom we then follow through time to figure out what they develop into later. Guys, chemical reactions are exactly the same. We have characters, we have reactants, and over time, that's the yields arrow, they turn into something new. The characters develop over time. Now guys, here's the additional layer that we're going to add today. Genres. You ready? A genre is a type of story. So guys, for example, this. If I were to tell you that the story you're about to read is a love story, it's a romance novel. Guys, you can make some predictions. Who are you going to meet in the beginning of the book? A man and a woman, right? And maybe you're going to have like a love triangle thing, but you're going to have a man and a woman, and at the end of the story, what's going to happen? Happily ever after, right? So guys, by simply knowing the genre, you can predict what's going to happen. Now guys, imagine this. Imagine that the story that we're reading is now like a dystopian novel, or it's like a murder mystery, or it's some crazy slasher book. Guys, when you meet all the characters at the beginning of the story, what's going to happen to most of them by the end? They're all going to die. So guys, the bottom line is this. You know from being readers that if you know the genre, you know the structure, and you know how the story is going to play out. Well guys, the same thing is true here. Let me introduce you. This is slide number 1. Guys, let me introduce you to the 5 genres of chemical reactions that we're going to talk about today. Single and double displacement, synthesis, decomposition, and combustion. And guys, by knowing these genres, you're going to be able to predict what happens in the story. Just like a romance novel, you know where it's headed. But guys, how do you know that something is a romance novel? And the answer is you look at the cover, right? And when you look at the cover, if there's some girl in the middle of a field in a long flowing white dress, you know by the end of the book she's going to meet Prince Charming, right? Guys, the idea is this. There are clues that tell you what kind of genre it is. Guys, these are those clues. This is what we're going to do today. We are going to define the genre. We are going to look at a general form of the genre. Then, guys, I'm going to give you a rule of thumb, something to look for to identify the genre. And then we're going to look at an example of the genre. But guys, here's the deal. All but one of these examples that we're going to talk about, you're going to do in lab when I see you after spring break. So guys, we're going to get started. But before we do, there's one other thing. Switch the slide, switch the page. Are you now on the next page? No, you guys are still there? Okay. Guys, please on this slide that's up on the screen, please write the words "only in lab." So what are we talking about? Well, guys, when we write balanced equations, we can add subscripts to tell us the phase. Solid, liquid, gas is SLG, S or L or G. And then, guys, AQ stands for aqueous, which actually means dissolved in water. So, guys, you will not do this in homework today, but you will do it in lab next time. Because you're doing the reactions, you're going to be like, oh, that's a liquid. You're going to put L. You get the, so not today. This is for Tuesday. You guys good? Okay. So here we go, guys. Genres. We are going to now talk about all 5 of these genres. But guys, I just got to warn you right up front. Some of this, well, let me say that differently. For some of you, this is really, really going to push the skills that you've developed over time. Guys, this is going to draw on a lot of the chemistry that you've learned over the last 6 weeks. So guys, stay focused, ask questions, and here we go. So guys, first of all this, in order to understand single displacement, you first of all need to understand what displacement means. So guys, watch the beaker full of pens. You ready? Here's the beaker full of pens, and now it's over here. That is not displacement. Guys, if I want to displace the beaker full of pens, I do that. What does displacement mean? To put something in its place. Guys, if it's single displacement, how many times does this happen? Once. So guys, single displacement is a single exchanging of partners. Guys, grab your periodic tables and now let's talk. The general form of this is this. A plus BC. Now guys, this is a general form, so let's talk about what it means. A is an element. BC is a compound. B bonded to C. So guys, the first question is this. Does this have it in your notes? Does it say A positive?
Yeah.
Is A a salt? I'm sorry, BC is the salt. Is A metal or a non-metal? How do you know it's a metal? Its charge is positive. So guys, A is a metal because it's positively charged. Now guys, BC, oh, you leaving? BC is a salt. So guys, when we write salts, which comes first? The metal or the non-metal? The metal. So guys, write this down with me. What that means is that B is positive and C is negative. They're always positive first. So now the question becomes this. Is positive A going to hook up with positive B or negative C? Positive goes to negative, so the A is going to hook up with the C. And guys, sadly, B goes home alone. Oh. It's the love triangle thing. A cuts in, grabs a hold of C, B goes home alone. But guys, this is not the only way that this can go down. Let's clean up the mess. And now guys, this. The other way this can go is A is negative. In your notes, given what you now understand, predict the products if A is negative. No. In your notes. So guys, still B is positive, C is negative. So guys, I think the majority of you understand that negative A is going to hook up with positive B, but did any of you pick up on the fact that it's not going to be AB? Why not? Yeah, guys, it's always positive first. So it's BA plus C. It matters. You guys okay? All right, so guys, moving along then. This is the rule of thumb. Anytime you see an element reacting with a compound, that will be a single displacement reaction. So guys, let's do this, and this is the reaction that you're going to do in lab. You are going to drop a piece of zinc into a test tube full of hydrochloric acid. The question is, what is it going to do? So guys, in order to figure out what it's going to do, just like here, we need to know the charges. So grab your periodic table, look up zinc on the periodic table, element number 30. What's its charge? Plus 2. So guys, do this. Write it down. Now if you look at hydrogen, probably most of you know this is plus 1. That means chlorine's got to be negative 1 because there's one of each. All right, so now guys, who's positive zinc going to hook up with? Positive hydrogen or negative chlorine? Chlorine, but be careful because zinc is plus 2 and chlorine's minus 1. So for those to balance, it's ZnCl2. Guys, details. Zinc is plus 2, chlorine's minus 1. But guys, now here comes the nice twist to the story. Hydrogen gets the boot. But hydrogen does not go home alone. Because, guys, we remember that iodine, bromine, chlorine, fluorine, oxygen, nitrogen, and hydrogen are diatomic. And so hydrogen hooks up with a buddy, and they hang out for the rest of the night. Let me finish. So now, guys, this. We've written the formulas, but now we need to balance it. We've got 1 zinc, so we're good. We've got 1 hydrogen and 2 hydrogens, so we need a 2. And then we've got 2 chlorines and 2 chlorines, and that balances. So, guys, questions about single displacement reactions? Dougie, James beat you. James, go ahead.
I'm thinking that,
You okay? Dougie, go.
So, when we did the pH, does that have all the other ones?
Yes. So you will never see iodine, bromine, chlorine, fluorine, oxygen, nitrogen, or hydrogen by themselves. They'll either be bonded to somebody else or they'll have a 2.
Actually, my question is
Yeah.
If chlorine and hydrogen weren't to be, didn't have the same amount there.
Right.
If it wasn't proportional.
Yeah. That's a great question. And so, James, when we talk about those proportions, we don't worry about the proportions when we write the formulas. When we write the formulas, we just balance charges. When we deal with the proportions is when we balance the equation.
Yeah, that's kind of what I'm asking about.
Yeah, and so we always do that when we balance the equation. Let's look at other examples. It'll come. All right, so guys, now looking on to double displacement reactions. So guys, if single displacement does it once, double displacement does it twice. You need to ditch the glasses. So guys, it goes like this. So the general form of this is AB reacts with CD. But now, guys, this. Here's your charges. Plus and minus and plus and minus. Predict your products. You should be able to do this. We have a double exchanging of partners. Predict the products. So guys, you're probably there, but let's talk about it. So positive A is going to hook up with negative D, so that would be AD. Then guys, negative B is going to hook up with positive C, but as Ty pointed out just a minute ago, it's always positive first, so our positive is C and our negative is B, and that's our double exchanging of partners. So guys, let's then talk about the general form of this, or the hint for this. And guys, what we've got here is a reaction where compounds are going in and compounds are coming out. So gang, now we're going to take a look at an example. But guys, this is not the example that we're going to do in lab next time. We will do a double displacement reaction, but not this one, because the lead is toxic and it's hard to dispose of. It's actually a really cool reaction because it makes this really vivid yellow precipitate. It's kind of pretty, but it's just too hard to dispose of, so we can't. But we can still balance it. So guys, in order to balance this, we need charges. Go find potassium, element number 19. What's his charge? +1. Then guys, iodide has to be -1 because they balance. But now guys, have this experience. Please don't ride on my coattails. Look at lead, element number 82. Yeah, we got a problem, guys. It's +2 or +4. This is the same problem that we solved 2 units ago by finding Roman numerals. So guys, that's what we're doing here. We are going to break this in half. We're going to look up nitrate, and nitrate is -1 on your polyatomic chart. -1 times 2 is -2, so this is +2. So guys, that means that lead is +2, and nitrate is -1. Now we trade partners. Potassium is +1, nitrate is -1, so we need one of each. That is KNO3. Then, oh please, go ahead, Soph. That's a brilliant question. And it kind of gets to what James was talking about a minute ago. So here's the deal. When we write the products, we don't care about how many we start with. We just care about charge. So K is +1, NO3 is -1. Yeah, there's 2 of them, but we don't care. If this is +1 and if this is -1, we only need one of each, and that's this. Yeah, so like if potassium was +2, then it would be KNO3 in parentheses 2, just like the good old days. Watch this. Lead is +2. Iodide is -1. So we need one of these and how many of those? Right. So this would be PbI2. Yep. Now we need to balance it. So guys, is this too messy? Can I balance it like this, or is it just mucky? We okay? So guys, we've got 1K, we've got 1K, we've got 1 iodide, we've got 2 iodides, bless you, so we need a 2. Then guys, we've got now 2 potassiums, so we need a 2. Then we've got 1 lead, 2 NO3s, and 2 NO3s, and that balances. Dougie. Great question. So this is the idea. Lead is +2. Iodide is -1. So when +2 and -1 come together, you need 1 lead +2 and 2 iodides -1 to balance the charge. Because this is +2, this is -1. So you need 2 -1s to balance the +2. Is that okay? Guys, how are we doing on displacement reactions? Same basic genre, right? We've got some moving of things, switching partners. Single displacement, it happens once. Double, it happens twice. Are we good? Okay. So guys, now we have the third genre. And guys, the third genre is actually the opposite of the fourth genre. So guys, synthesis is a reaction that puts parts together. You're like, oh, that makes sense. Synthetic means man-made. Guys, that's what we're doing. We're taking bits and putting them together. So guys, the general form is this. A plus B, but if they're putting stuff together, what's the product? It's just AB. Do you get the idea? That, guys, in a synthesis reaction, the bits are just coming together to make something bigger by putting the bits together. So, guys, at the end of the day, the general form of this, which it's not going to let me do, just a moment. Guys, the rule of thumb for this is one product. Guys, if you have a reaction that forms one product, that will be a synthesis reaction. So, guys, this is actually the synthesis reaction we're going to do. And we were talking about, it's one of the few things that my AP students really remember from the year before. They're like, oh, you're going to want to do this reaction like 3 to 5 times. This is the reaction we're going to do. Hydrogen and oxygen. Because what does it make? Water, right? So water is H2O. Do you have that in your notes? Yeah, good. But guys, notice what else it makes. It makes energy. Guys, when hydrogen and oxygen make water, it releases energy. There's a name for that. It's called exothermic. So guys, anytime you have a synthesis reaction, it will always be exothermic. Now we need to balance it. 2 hydrogens, so 2 hydrogens, 2 hydrogens, so that's good. 2 oxygens, 1 oxygen, so we need a 2, but then that gives us 4 hydrogens, so we need a 2. That is a balanced synthesis reaction. So now, guys, why is this reaction so interesting? And the reason is because it explodes. Guys, when you do this reaction on Tuesday, you're going to have a reaction literally in your hand and it's going to blow up. And then you're going to want to do it again and again. So guys, the energy that comes out of this comes out in the form of heat, fire, and sound. It's literally a little explosion. And we're going to do that on Tuesday. So, synthesis reactions put things together. So now, guys, this. The opposite of synthesis is decomposition. Now we're taking something and breaking it apart. But guys, check this out. The rule of thumb, do you have this? Only one reactant? Hey, buddy. But guys, it goes like this. Be careful, because just watch the screen. So guys, this is the synthesis reaction we just looked at. Hydrogen and oxygen on the left, water on the right. But guys, watch the screen. We're now going to turn this synthesis reaction into a decomposition reaction. You ready? Watch close. Do you get it? Guys, draw that in your notes. What I would do is I would just draw arrows showing that you're flipping sides. So if synthesis puts it together, guys, decomposition takes it apart. So now we've got water breaking into hydrogen and oxygens. But guys, there's a name for this. The name for this process, if it'll let me do this, is called endothermic. Guys, this is an endothermic process. That means that energy is going in. But guys, here's the problem. In lab, where do we get energy from? What's our energy source? Bunsen burners. But guys, here's the deal. You know that a Bunsen burner will not work. Because if you put water over a Bunsen burner, it doesn't turn into hydrogen and oxygen. What does it do? It boils. But guys, the things that are being given off in steam are still water. So heat will not cause this to happen. So what will? Do you guys know? Electricity. Guys, if you pass electricity through water, it will actually do this. So here's how this goes. Guys, I used to do this as a demonstration, but this glass piece right here costs about $350, and I had a student a few years ago borrow it from me to do a science fair project, and he broke it. So he tried to silicone it back together, and that didn't work. But guys, basically what we've got here is we've got 3 vertical tubes. They all connect down at the bottom, but at the very bottom, you'll notice that there are wires sticking in the bottoms of the outside tubes. Here's the way this goes. You fill this thing up with distilled water, and then you hook it up to a battery. And when you flip the battery on, current flows through the water. But guys, can you see the bubbles? What do you notice about the bubbles on the left compared to the right? There's more. Guys, look at all the bubbles that are on the left compared to the bubbles that are on the right. Guys, any thoughts on why? Why would there be more bubbles on the left, Luke? Say it again. Not quite. Why would there be more bubbles on the left? Go ahead, Jonathan.
Because there's more hydrogen.
Because water is H2O. So guys, when this breaks into gases, you have twice as much hydrogen as oxygen. So what that means is that this is the negative side of the battery, and the positive hydrogen is attracted to it. And this is the negative, or wait, what did I say? This is hydrogen negative. This is the positive side of the battery, and the negative oxygen is attracted to it. But literally, guys, water is H2O, which means there's twice as much hydrogen as oxygen, and you can actually see this when we go to the top. Guys, there is this much hydrogen and there is this much oxygen. It's literally double, proving that water is H2O. You get the idea? Guys, we have one more genre to go, and we're going to work on some homework. So guys, the last genre that we need to talk about is combustion. So guys, combustion reactions... No, you're good. Combustion reactions, y'all, are reactions of hydrocarbons, not carbohydrates. Carbohydrates are carbon and water. This is a hydrocarbon. And we write it like this. C, some number of C's, X, hydrogen, some number of Y. So it's some number of carbons, some number of hydrogens. And guys, when this reaction happens, it reacts with oxygen and it always forms carbon dioxide in water. So guys, looking at the example, it simply goes like this. So guys, here's the mistake you're going to make. You're going to be like, oh, I got to look up charges and carbon is this and Guys, you don't have to do any of that. Anytime you see carbon and hydrogen together and oxygen, you don't have to think. You just have to write down carbon dioxide and water, and you're done. That's it. It's always carbon dioxide and water. Yeah. We do. One carbon, 4 hydrogens, 2 hydrogens. So we need a 2. And now over here we have 2 plus 2 oxygens. So we need 2 there to have 4 oxygens. But guys, that's it every time. So guys, that's it. We now have 5 genres of reactions. Guys, please understand, there are thousands. You only need to know 5. These are the common ones in general chemistry. But guys, the question then becomes, what are we going to do with this? Any questions? Guys, grab your homework. So we are now on homework assignment number 2. So guys, look at this with me, and we're going to get some of this done. So guys, looking on the front of assignment number 2, which apparently I can't find. There it is. So guys, notice at the top, you've got your 5 genres, right? Now look at number 1. You have got a compound breaking into elements. What is that genre? Decomposition, right? DEC on the line. Then guys, your next genre, you've got compound trading partners to form 2 new compounds. Double displacement. Write it down. Now guys, number 3, you have 2 elements coming together to make a compound. Synthesis, write it down. Number 4, compound forming 2 new compounds by trading partners. Double displacement. Number 5, an element and a compound. And then guys, the products, that element zinc hooked up with the SO4 and copper got kicked out. Single displacement. You see how that works? Guys, let's go to the back. You can do the rest of that in a minute. Let's go to the back. And guys, this is where this gets a little interesting. We're going to do number 1 together. Right? Guys, it reads like this. All that you are given is the names of the reactants. You really don't know what they are. You certainly don't know what they're going to do. You don't know the genre. So what do we have to do first? We've got to figure out what our reactants are. So guys, grab your periodic tables, grab your ion charts, and let's do this. Aluminum is element number 13. It is Al with the +3 charge. I'd strongly encourage you to do this the way I am. Then guys, sulfate ends in 8. That means it's on the yellow sheet. Sulfate is SO4 -2. Now guys, where do 3 and 2 meet up? At 6. So that means we need 2 aluminums and 3 sulfates in order to balance the charge. Now guys, moving on to calcium phosphate. Calcium is element number 20. Its charge is +2. Phosphate, as in 8, is on the polyatomic ion chart. That would be PO4, and it is -3. Once again, 2 and 3 meet up at 6. So now we need 3 CAs and 2 PO4s. So now guys, we've got our reactants, and this now allows us to identify the genre. So let's think about it. Guys, go through the list. Can this be single displacement? No, it's not an element in a compound. Could it be double displacement?
Yes.
It's possible. Could it be synthesis? In theory, yes. We could jam all of these parts together. But guys, that's not what's going to happen. Could it be decomposition? No, we have more than one thing. Is it combustion? Heck no. It's not a hydrocarbon and oxygen. So guys, the only reasonable choice is double displacement. So we write that on the line right here.
We have to write the rest of the equation.
Oh yeah. But guys, we know the genre. We know that it's double displacement. So now guys, we've got to trade partners. But guys, look. If you did this the way I did, you've already done the legwork. Because look at what you know. Let's see if I can switch colors. Guys, you know that aluminum is +3. And you know that phosphate is -3. The positive and the negative are going to hook up. But if aluminum is +3 and phosphate's -3, you only need 1 of each. And now guys, the other rearranging of partners. Calcium is +2 and sulfate is -2. You only need 1 of each, so your other product is Ca, 1 calcium, and SO4, 1 sulfate. Now guys, all we got to do is balance it. We've got 2 aluminums, so we need 2 aluminums. We have 3 SO4s, so we need 3 SO4s. Now we have 3 calciums, and we have 3 calciums, and now we have 2 PO4s, and we have 2 PO4s, and that's balanced. That's what this page is all about. Now, guys, one other thing to mention, and this is not because you're just general chemistry students. Guys, even in AP, the one skill that you will not develop is the ability to predict the products of decomposition. Imagine this. If you have a rock and you make it decompose, you hit it with a hammer, you don't know what it's going to break into. Guys, the same thing is true here. So number 3 is decomposition. I need to tell you that the products are table salt and oxygen. I would encourage you to write that down. There's no way for you to know except for me to tell you. Then, guys, number 6, your products are water and sulfur dioxide. Again, guys, there's no way for you to know. I just have to tell you. Then number 10 is also decomposition. It produces copper metal, water, and oxygen. Bless you. And then, guys, finally this. Number 12 is really tricky. Let me just tell you up front, this is a single displacement reaction. So, guys, there you have it. The remainder of the day is yours to chip away at these. The answers are on the wall. They're also posted online. And so, guys, we're going to get started. Eli, just a second. Let me stop recording, and then we'll do questions.